So we face the challenge again, once again, of what is a tangent line. And we thought we had left that in Calculus 1, and now we see questions coming back on that. And quite frankly, the question, what is a tangent line? What do we mean by that is at the heart of about the first 2/3 of Calculus 1, and it's going to come back, and we really want to look at it correctly for us to be able to walk into the last third of Calculus 2. It's a big deal. So let me kind of go over what you should be thinking about when you see tangent line. Here I've defined a piecewise function in Mathematica, a little bit of sine up to a half, and then a little some other kind of sine up to from a half to 3/4, and then just a line. We plot it. I make the line a little thicker so we can see it. I make sure that when it does this jump here, this jump discontinuity, it doesn't draw a line in there, and I hate that when the calculators do that. And this is all just to get that big red dot right there. So usually you won't be writing code like this, but anyway, you definitely will want to learn how to use a piecewise function. So what do we have here? Well, we have a discontinuity here, and here it's continuous, but it's kind of pointy. If you zoomed in there, it would look kind of flat there, and it would have a slope of -2 there. Tangent lines are about the idea of limiting, of zooming into curves and having this property that sometimes when you zoom in, if you were a little bitty microbe living on that curve, your world would seem like a line. It would seem to have constant slope. Let me show you what I mean. So my big red dot right here is at 0.4, so I'd like to zoom in at 0.4. So I'm going to, we've defined f, remember, I'm going to zoom in here. So let's go like 0. Blah, blah, blah. 0.3 to 0.5, okay? Move out of the way and zoom in. Now, so we're going from 0.3 to 0.5, and there's our red dot at 0.4, and it's a nice curve right here. Now, let's get much closer. Let's zoom in to like 0.39. Of course, much closer is relative, right? That's one of the big ideas behind limits. 4, 1. Now, so if you were a microbe and you were only like 0.001 wide, so you lived right in here, you would say that your world was a line. Now the question is what is this line that I see at points on the curve sometime when I zoom in? Sometimes not. Sometimes the curve breaks. It's not continuous. Or even if it is continuous, it doesn't look like a straight line right there. But sometimes it does look like a very straight line, and the question is what line is that? Okay, so let's take this zoomed in picture and let's ask ourselves, how do I define a line? Well, what we want here is the point slope form, and I am sure that you have this tattooed somewhere, but in case you don't, there it is. So what do we need to determine a line using the point slope form? Well, we need a point on the line and the slope of the line, and the slope's the same everywhere. I hear my children and wife playing. So what is this point right here? Well, the x value is 0.4, and the y value looks like to be a little bit bigger than 0.95, and more specifically the x value, this x0 is 0.4, and the y value is given by f of 0.4. That's the whole idea of being a point on this graph. So if we plug those in, that's what we have. Now, great, wonderful. We haven't used calculus at all, except we've zoomed in, so we've used the graphing abilities to zoom in, so it feels sort of like a limit. The question is what is the slope there? What is the slope of this line? Well, we could pick 2 points close to this line and get a nice approximation of the slope. But what I want to do is pick points closer and closer, and that's the idea behind melding limit and the difference quotient, the change in y over the change in x, and take a limiting process, f of x plus h minus f of x over h. As h goes to 0, that should ring a bell, and get the derivative. And so you get a new function here, the derivative that tells me the slope that if we were a little microbe, we would see right there of this line. So it's the derivative of f at 0.4. Now, if I move this over, so I'm going to Move that over, copy and paste it. So I add it. It was subtracted, so I add it. And this is the line that the microbe sees at that point. Maybe not another point, but at that point, that's what the microbe sees. So let's just, let's see what that is. So I could go y equals f of 0.4, and Mathematica knows what f is, so it would calculate it for me. I've defined it earlier. Plus, and Mathematica, if I take a simple function and write f, calling it f, and I put a prime on it, it knows how, it will at least try to take the derivative, times x minus 0.4. Let's see what we have here. Hey, J-Man. All right, so let's run that. What do we have? Boom. That's a line. That's a line. Question is it the line we want? All right?
Give me some skin.
I'll give you some skin. There you go. All right. So I'm going to copy this, and I'm going to go back to, there we go. I'm going to go back to this function where we were plotting this, and I'm going to plot the regular function along with the expression for the line, the functional expression for the line. So I'll put comma, and there it is. Except the variable I'm using under this command is t. So there, this is going to plot f of t from 0 to 1, and it's going to plot this line from 0 to 1. Okay, let's see what we get. Boom. Now, you look at that, you should say, yep, that is what I mean by the tangent line. It touches there at just one point, da 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 da. So you have all these kind of ethereal metaphors in your head, which is how we understand anything. But in mathematics, we also have the definition. And so this is what we mean, that the tangent line at a value x equals a of a function y equals f of x, if it exists, it may not exist, has to definitely be continuous, but even that's not good enough. But if it exists, what we mean by it, what we define by it is it's that linear approximation, it's that line that you would see if you lived right there at that point. That linear approximation given by y equals, the constant would be f at that point, the slope would be f prime at that point times x minus a, and that will give you the formula for, that is the formula for the tangent line if it exists. I hope that helps. I know I went longer than 5 minutes, but it's a, yeah, we just did 2/3 of, well, we didn't, but we did a lot in, looks like 7.5 minutes, and that is enough. Beautiful stuff. I hope that helps.